Okay, I hope everyone can hear me online as well. Yeah, seems to work. Okay. Then, well, a warm welcome from me as well. After getting the organizational details out of the way, I think we are ready to dive into some more technical stuff and see the first performance related contents of the workshop. I'm Christian. I'm a PhD student here in the RWTH HPC group, and I'm mainly responsible for the monitoring of our system, like performance monitoring, not as we saw before with counting of core hours, but how the system performs, what kind of resources you are using, and how good you are using them. And that's why I want to talk to you about verifying GPU performance with the RWTH job monitoring. First, small motivation. Of course, we have this new shiny cluster which gets replaced every 5 years in the best case, and yeah, our new system is quite new. What does it offer all of you? I would say better performance, so that's really good. You can do more work with the same amount of core hours or GPU hours in our case. For us operators, it's important because we can provide more energy efficient system. That means our electricity bill doesn't skyrocket with every new system. But of course, we are all here today in a workshop to optimize our code for the new hardware. So you need to port your code over to a new system. That means, yeah, we're working in depth with some codes. And that can be kind of a pain, but that's why we are here today to help you. So let's see what I've brought with me today. So first I'll talk about accessing our monitoring system, then detecting some misconfigurations and giving you some examples how you can use it also today, and finish just with a simple call to action. So every one of you already should have access to the monitoring portal, whether you have used it or not. The web monitoring portal is available under this URL, perfmon.hpc.itc and so on. Perfmon for performance monitoring, of course, and when the slides are online, you can also find these links to the online documentation, or just Google performance monitoring or job monitoring RWTH in Google, and this should be one of the first pages to pop up. When you go to this URL, you'll be greeted with a lovely login screen, just redirecting you to a single sign-on. Be aware, this are the standard single sign-on credentials you know from other services, not your HPC account. But this technical detail out of the way, you'll be greeted with a history of your finished and running jobs. So this is just a table with the job IDs, your job names, the partitions you submitted, and so on, like the basic job information. And here you have different options to filter by cluster partition, depending on whether you want to analyze CPU or GPU jobs, sort by runtime, to ignore, for example, small test cases that you have used, and to see even jobs further back in the history. You can here at the top right increase time range. So the default should be something like 90 days, which should be sufficient for most analysis, but you can go further back in to the past. Then to access the job details that we've recorded during the execution of your job, simply click on any of the lines, and then you'll get a pop-up in a new window, and this will show more details on your current job. To just highlight a few things here. On the top left, you can see some metadata about the job as we saw on the table before, like the project, the partition, and how many cores you've allocated. Then we've added a short energy consumption summary, which is estimated based on the monitored data, and obviously all the other stuff that you may or may not see here on this slide, because When you actually scroll down, there's a lot more information shown there. You can switch to single or multi-host view depending how many nodes you use. You can select different hosts here at the top and select from the CPU specific ones with control or command click depending on your operating system. A few caveats before we go into like the details how to use it. A note on the sampling frequency. We only sample once per minute. That has the advantage to have almost no influence on the application runtime. That means you get the core hours you actually allocated. But the challenge is that short application stages can be missed. So to actually use this monitoring system, you should usually have runtimes of at least 15, but better 30 minutes to have sufficient number of samples during the application runtime. Second, the sampling quality can differ depending on the metrics that you look at. For example, for the floating point operations per second, the power and the memory bandwidth, we can only sample that for a single second before we do not collect anymore. And be aware that this data is missing, or if you want to do your own measurements, you need to specify specific slurm option here, --HWCTR for hardware counter, and then with one of the options provided to the right. For other metrics, we have continuous measurements, but only sample the current counter value. That's for fabric, so network communication, Lustre, so Parallel I/O, which we will have a focus session on Wednesday, and NFS, so for your standard file system, home file system. For other metrics like the CPU usage, GPU usage, and memory, only the current value is recorded. So this is really also sampling. You don't get a continuous measurement. Also, a few caveats on, since we are on a shared system, we have shared node usage sometimes. You can force exclusive node usage with this exclusive flag. However, note that the consumed core hours will significantly increase. But this gives you an exclusive view on the monitoring data if you specify this. Otherwise, data may be influenced by the behavior of other jobs. So the data that you show might not be only from your job, but other jobs running on the same node concurrently. A few note on these power and energy measurements. I think the links here help because these are also only sampled. Some funding agencies might require you to specify energy measurement or energy estimations. Here you can find a few more details what the caveats for these technologies used for measuring this are. I don't want to go into more detail here, just the links are available, and also in the monitoring portal these links are given. So this is like the overview. Now let's see what we can actually do with this. First, I've brought an example, a job analysis here. So we can see we have here, we're starting with a CPU job. This can also be seen here where we don't have any GPU data. Then this no data will show up. And here we first focus on the CPU usage, from which is from 0 to 100 simply for each of the cores on the system. And we can see that we have correctly allocated 69 cores, which is a current core count of CLAIX 2023. However, in the mean, this is this gray area here, we only have 50% mean CPU usage. This here, of course, this is an example. And yeah, you might see this when you transition from CLAIX 2018 to CLAIX 2023, since the old system only had 48 cores per node. So you might have hard-coded somewhere the number of threads that you use or the number of processes which are specified in a Slurm or MPI. So here you can have a basic verification that you actually use the resources that you allocated. So yeah, takeaway is to look at any of these hard-coded values. These are some examples. Other things can go wrong, but these are the most common things that we also actually see in production. Some people just don't adjust this when going to a different system. Since we are also specifically focused on GPU today, they've also brought us GPU examples, so we can see that we actually use the correct partition here. However, our job actually timed out, although we were sure that it would not, based on like small tests that we've run. Then we can scroll down. So this is a GPU-specific view, which is available. So here we can see GPU utilization on the top left, GPU memory usage, and the PCIe transfers to and from the host to the GPU for each of the available GPUs. And here we can also again see for the GPU utilization that we only have a mean of 25%, so only 1/4 is used, which is the problem here. For GPUs, there might be some other problems other than simply saying you have not used enough GPUs. For GPUs, it's common to restrict the availability of GPUs, for example, with CUDA visible devices or something. If, for example, if you have tested that on a front end where you might need to avoid other users, who concurrently allocate GPUs. In the back end, you don't need this, but that's why setting CUDA visible devices to something can actually lead to some misconfiguration of your job. To actually check the allocated CPUs and GPUs in the execution script of your job, you can add this command as control show job with your job ID and then -- details. Then you will see the actually allocated GPUs and you can filter interactively based on this. For some ideas for further, more detailed analysis, I've brought here an example for where we compare the memory bandwidth. For example, we knew from CLAIX 2018 that we are usually achieve around 200 gigabytes per second of CPU memory bandwidth. On the new system, we can see we only have 60. So this should be immediately a red flag. That depends obviously on your experience with using your codes, whether you have used them on the old system, whether you've got some previous runs which behave better or just different from the new runs. So, for example, you might have some previous experience with a job and say, usually my bandwidth is 90% of the peak, or before like more than 200 floating point operations per second occurred, something like this. And then you can compare this over time, whether something changes significantly. Regarding these expectations for CLAIX 2023, it might be difficult, but that's why we are here. So talk to us if you are unsure and whether you observe some deviations from previous results. For GPUs, I've brought another example which involves the PCIe transfer speeds. Here I've brought two examples, one for which uses pageable memory, which transfers with 10 to 25 gigabytes per second, and another example which uses pinned memory using 45 to 60 gigabytes per second. So this might be for performance regression. You might see if a default in a framework changes or something. So this might be useful to look at, maybe not all of the time, but once a month or something if you want to ensure that your jobs run sanely. I mean, this is all interactive, so it's not a huge workflow like setting up and using it. It always runs in the background. So you can just go online onto the webpage when you have time and simply look at it. Also, some useful things to compare your expectations to are like the GPU memory usage, which you might be restricted in as well for your machine learning tasks, or the portion of CPU time that is used during your job, for example, to load any data from disk. If this is much larger than you expected, it's a good idea to also talk to us in finding options. how this can be reduced, because if the CPU is working, the GPU is usually idling, so that's undesirable for a large GPU application. And otherwise, network and storage utilization are also common things to look at. So these are just some of the high-level examples, and from my side, there's nothing more to say. Just simply download the slides from the aiXcelerate website, then you can click the icon or go to the link directly, and let's discuss your results in the next days. And yeah, if you have any ideas, we also welcome any feedback, and we'll try to integrate it as soon as possible. Since this is like a developing portal, developing like project, we are always happy for feedback and look forward to working with you. So thanks for your attention.